virtual machine architecture. Here you can see architectural diagram of Java virtual machine. The Java command starts a Java application. It does this by starting Java virtual machine JVM, loading the specified class and calling that class's main method. The method must be declared public and static. It must not return any value, and it must not accept a string array as a parameter. So here by using Java command we are loading JVM to execute the main method in this my program class file. We are focusing on class file. A class file consists of a stream of 8-bit bytes. All 16-bit, 32-bit and 64-bit quantities are constructed by reading in 2, 4 and 8 consecutive 8-bit bytes respectively. Multi-byte data items are always stored in big endian order, where the high bytes come first. In the Java SC platform, this format is supported by interfaces java.io.dataInput and java.io.dataOutput, and classes such as java.io.dataInputStream and java.io.dataOutputStream. You can see the structure of a class diagram here, the structure of a class file here. The magic item supplies the magic number identifying the class file format. The values of minor version and major version items are the minor and major version numbers of this class file. Likewise, there are other fields: constant pool count, constant pool, access flags, this class, superclass, interfaces count, interfaces, fields count, fields, method count, methods, attributes count and attributes. This is a sample display of a class file in a text editor like Notepad in Windows. Now the class file is moved to class loader subsystem. Java's dynamic class loading functionality is handled by the class loader subsystem. In this diagram you can see local system here, class file is here, and read class file from local system to class loader subsystem. Then it moved to load class files to JVM memory area. JVM memory area is represented here in this diagram. Now we are focusing on loading. Classes will be loaded by this component. For example, in source code, this is a sample class file named dog. We can see 3 fields here: breed, age and color, and there are 3 methods: barking, hungry and sleeping. Now we are focusing on Bootstrap class loader. In loading, Bootstrap class loader is responsible for loading classes from the Bootstrap class path, nothing but rt.jar, i18n.jar and others. rt.jar mean root jar file, which is located in lib directory, which is in JRE directory, and i18n.jar is responsible for internationalization. In this diagram you can see a class loader delegation algorithm. Bootstrap class loader is communicated with extension class loader through delegates. For example, java.learn package is loaded through Bootstrap class loader, and packages like java.net, java.util, java.io are loaded through Bootstrap class loader, and this mentioned packages are in root.jar file. If no purported representation of a class is found, loading throws an instance of class not found exception. Now we move to extension class loader. Extension class loader is responsible for loading classes which are inside ext folder. Ext folder is in lib folder, which is in JRE directory or folder. Extension class loader is communicated with Bootstrap class loader and application class loader through delegate pattern. If you have a user created jar file called area in extension folder, for example, extension folder, the classes in the area.jar file will be loaded through extension class loader. As an example, if no purported representation of class is found, loading throws an instance of class not found exception. Now we move to application class loader. Application class loader is responsible for loading application level class path mention, environment variable, etc. Application class loader is communicated with extension class loader through delegates. By default, class path is set to the current directory of the application. We can set class path through set class path command. This example is in Windows, and here class path is set to C Java and my classes folder. And if you have a class file name my classes in this folder, classes in the my classes jar file will be loaded through application class loader. If no purported representation of class is found, loading throws an instance of class not found exception. After loading, we are considering about linking. Linking a class or interface involved verifying and preparing that class or interface its direct superclass, its direct super interfaces, and its element type if it is an array type if necessary. Resolution of symbolic references in the class or interface is an optional part of linking. Now we are focusing on verify in linking. Verification ensures that binary representation of a class or interface is structurally correct. Verification may cause additional classes and interfaces to be loaded but need not cause them to be verified or prepared. In this diagram you can see verify T class, and here in this, according to this diagram, the all super types of T have been verified. If the code has been built using Java 11 but is being run on a system that has Java 8 installed, the verification phase will fail and it throws verify exception, for example. If the binary representation of a class or interface does not satisfy the static or structural constraint, then a verify error must be thrown at the point point in the program that caused the class or interface to be verified. If an attempt by the Java virtual machine to verify a class or interface fails because an error is thrown, that is an instance of linkage error or a subclass, then subsequent attempt to verify the class or interface always fail with the same error that was thrown as a result of initial verification attempt. After verify, we move to prepare. Preparation involves creating the static fields for a class or interface and initializing such fields to their default values. This does not require execution of any Java virtual machine code. Explicit initializers for static fields are executed as part of initialization, not preparation. Here you can see preparation of T class in this diagram, and all super types of T have been prepared here according to this diagram. JVM allocates memory for the variable enabled and set its value to the default value for a boolean which is false. This is static field, and so even though it's assigned to true, in this space enabled is assigned to false value which is default for boolean. After prepare, we move to resolution. Linking is moving to resolution. Resolution is the process of dynamically determining concrete values from symbolic references in runtime constant pool. All symbolic memory references are replaced with the original references from method area. This is the method area, and in this diagram, resolve call of a method defined in T, you can see here. If you have references to other classes or constant variable present in other classes, they are resolved in this space and replaced with their actual references. Here we can see a instance of class A is created, and there's a variable A, and So then this variable will be resolved in this pace. If an error occurs during resolution of a symbolic reference, then an instance of incompatible class change error or a subclass must be thrown at the point in the program that directly or indirectly uses the symbolic reference. If an attempt by Java Virtual Machine to resolve a symbolic reference fails because an error is thrown, that is an instance of linkage error or a subclass, then subsequent attempt to resolve the reference always fail with the same error that has thrown as the result of the initial resolution attempt. After linking, we class loader subsystem move to initialization. Initialization of a class or interface consists of executing its class or interface initialization method. Here all static variables will be assigned with the original values and static block will be executed. The variable enable was set to its default value of false during preparation phase. In the initialization phase, the variable is assigned its actual value of true. You can see now it was false in this phase prepare, and now it's the actual value is assigned to the static variable enabled here. If the class object for class is in an erroneous state, then initialization is not possible, and it will release initialization lock and throw a no class def found error. The class or interface initialization method must have completed abruptly by throwing some exception. If the class of exception is not error or one of its subclasses, then create a new instance of this class exception in initialize error with exception as the argument, and use this object in place of exception in the following step. Class loader subsystem is communicated with runtime data area, and it's linked with runtime data areas, and we are now going to consider about runtime data area. Runtime data area is linked with execution engine and native method interface also. Java Virtual Machine defines various runtime data areas that are used during execution of a program. Some of these data areas are created on Java Virtual Machine startup and are destroyed by only when the Java Virtual Machine exits. Other data areas are per thread. Per thread data areas are created when a thread is created and destroyed when the thread exits. In this diagram you can see heap memory and parameters like XMS likewise, and you can see here young generation and old generation in heap memory, 2 from sections like 2 from Eden old, and here non-heap memory in permanent generation, code cache and permanent. This is on these different data different areas. Starting a JVM with 256 MB of initial and minimum heap size, and will allow the process to use up to 2048 megabyte of memory by using this command. And Oracle recommends settings the minimum heap size equal to the maximum heap size to minimize garbage collections. Now we are focusing on method area in runtime data areas. Java virtual machine has a method area that is shared among all Java virtual machine threads. The method area is analogous to the storage area for compiled code for a conventional language, or analogous to the text segment in an operating system process. It stores per class structures such as the runtime constant pool, field and method area, and the code for methods and constructors, including the special methods used in class and instance initialization and interface initialization. Here you can see method area, and you can see runtime constant pool, field, method area, code, and areas also in this diagram. In this code example, the field level data such as name, age, and the constructor details are loaded into method area here. Here the constructor details are also loaded into method area. And if memory in the method area cannot be made available to satisfy an allocation request, the Java virtual machine throws an out of memory error. Heap area. The Java virtual machine has a heap that is shared among all Java virtual machine threads. The heap is the runtime data area from which memory for all the classes, class instances, and arrays is allocated. In this diagram you can see heap area here. It has young generation, old generation, and survivor, zero survivor 1, and Eden, tenured and tenured areas. In this example, the instance of employee is loaded into heap area. Here, if a computation requires more heap than can be made available by the automatic storage management system, the Java virtual machine throws an out of memory error. Now we are focusing on stack area. Each Java virtual machine thread has a private Java virtual machine stack created at the same time as the thread. A Java virtual machine stack stores frames. A Java virtual machine stack is analogous to a stack of a conventional language such as C. It holds local variables and partial results and plays a part in method invocation and return. Because the Java virtual machine stack is never manipulated directly except to push and pop frames, frames may be heap allocated. The memory for a Java virtual machine stack does not need to be contiguous. In this diagram you can see a stack here under native area, and if the computation in a thread requires a larger Java virtual machine stack than it is permitted, the Java virtual machine throws a stack overflow error. If Java virtual machine stack can be dynamically expanded, an expansion is attempted but insufficient memory can be made available to effect the expansion, or if insufficient memory can be made available to create the initial Java virtual machine stack for a new thread, Java virtual machine throws an out of memory error. You can see there can be threads in stack area, thread 1, thread 2, and number of threads. Stack area is a thread safe since it is not shared resource. It's not a shared resource. You can see threads here in this diagram. Now we are focusing on stack frame. Each frame contains last in first out stack known as its operand stack. The maximum depth of the operand stack of a frame is determined at the compile time, and it's applied along with the code for method associated with the frame. Here you can see invocation process of a method called add two types. This is the basic frame structure here in this diagram, and these are the frames for add and print. You can see here for the invocation process of add two types, before invocation you can see the frame here. Two variables are two values here, 1 and 8.88, and after invocation you can see here, and when after add two types returns, you can see the value the added value is here 89.88. Here we are considering a method called calculate normalized score. To describe stack frame, and now we are considering local variable array Each frame contains an array of variables known as its local variables. The length of the local variable array of an frame is determined at the compile time and supplied in the binary representation of a class or interface along with the code for the method associated with the frame. Here you can see local variable array in this frame for add two types method. In this method, local variables like answers and score are stored in local variables array here. Operand stack. Each frame contains a last in first out stack known as its operand stack. The maximum depth of the operand stack of a frame is determined at compile time and is supplied along with the code for the method associated with the frame. Here you can see operand stack here. For example, intermediate operations like push, max score, push, min score, push subs are in operand stack. Here you can say intermediate operations are there. These are also performed in operand stack. In this example, you can see Java virtual machine instructions are given here. iload 0, push int in local variable 0, iload 1, push the int in local variable 1, I add pop to int, add them, push result, I store 2, I store underscore 2, pop int, store into local variable 2. And related method is given here. Frame data. All symbols corresponding to the method is stored here. In the case of any exception, the catch block information will be maintained in the frame data. Here in this diagram you can see the method frame data here. These symbols are stored here, and here catch block information also maintained in frame data. Now we are discussing about PC registers. Java virtual machine can support many threads of execution at once. Each Java virtual machine thread has its own program PC program counter register. Each thread will have separate PC registers to hold the address of current execution instruction. Once the instruction is executed, the PC register will be updated with the next instruction. You can see number of PC registers here, and in this diagram you can see the PC registers here. for each threads. Now we are focusing on PC register for a thread. At any point, each Java virtual machine thread is executing the code of a single method, namely the current method for that thread. If that method is not native, the PC register contains the address of the Java virtual machine instruction currently being executed. If the method currently being executed by the thread is native, the value of the Java virtual machine's PC register is undefined. The Java virtual machine's PC register is wide enough to hold a return address or a native pointer on the specific platform. Here in this case, PC will be 0, program counter will be 0, and JVM won't print the trace. JVM usually report a native stack trace in the crash dump. Here you can see in the C function function pointer is assigned to 0 and then it's called, so program counter will be 0. Now we are going to discuss about native method stack. An implementation of the Java virtual machine may use conventional stacks, colloquially called C stacks, to support native methods. Methods written in language other than Java programming language. Native method stacks may also be used by the implementation of an interpreter for the Java virtual machine's instruction set in a language such as C. Java virtual machine implementations that cannot load native methods and that do not themselves rely on conventional stacks need not supply native method stacks. If supplied, native method stacks are typically allocated per thread when each thread is created. In this diagram you can see a native method stack here. In this diagram you can see stack frame here is called another stack frame, and this Java method invokes a native method, so it moved there, and this C function invokes another C function, can be for example, and this C function invokes a Java method, so it's moved there and call contact the Java stack frame, and this is the current stack frame here. This is the native method stack here. Here in native method stack, here you can see native keywords is used here, so it provides the method definition only for the method signature of display hello world, and it does not provide any implementation. Here in static block it's called load library, and it's load the appropriate library name hello in native language. Here you can see function signature in native. See display hello world here, and here you can see the implementation hello world, and display hello world here, and stuck hello world this and print hello world here and return in C. If the computation in a thread requires a larger native method stack than is permitted, the Java virtual machine throws a stack overflow error. If native method stacks can be dynamically expanded and native method stack expansion is attempted but insufficient memory can be made available, or if insufficient memory can be made available to create the initial native method stack for a new thread, the Java virtual machine throws an out of memory error. And here this implementations will be loaded in native stack. Now we are focusing on execution engine. It access runtime data areas and can access also access native method interface. The bytecode which is assigned to the runtime data area will be executed by the execution engine. Execution engine reads the bytecode and executes it piece by piece. Now we are focusing on interpreter in execution engine. It reads the bytecode and interpret, convert into the machine code, native code, and executes them in a sequential manner. This component runs the application from the command line by accepting a file name argument. The problem with the interpreter is that it interprets every time, even the same method multiple times, which reduces the performance of the system. To overcome this problem, JIT Compiler is introduced in version 1.1. Here you can see the Java source program is here. For example, it's compiled and it's produced the bytecode here, and this interpreter interpret the relevant machine interpret into the machine code related to Win32 platform, and this interpreter convert this class file instruction into Solaris machine code instructions, and this interpreter convert Java bytecode instructions into macOS machine code instructions. For example, this method will be interpreted piece by piece through interpreter. If the no class def found error will occur when the interpreter cannot find the file containing a class with the main method. Now we are focusing on just-in-time compiler. The execution engine will be using the help of the interpreter in converting bytecode, but when it finds repeated code, it uses the JIT just-in-time compiler, which compiles the entire bytecode and changes it to a native code. This native code will be used directly for repeated method calls, which improve the performance of the system. In this diagram you can see Java source code is here. At the compile time, is create after compilation is create bytecode, and JIT compilation occurs the first time a method is called, and only if it is called. And here JIT compiler create a native code which is cached in the memory for the repetition if needed. You can see here exception in JIT occurred, JIT compiler occurred here. Here in a VM state, it indicates that the JIT compiler is compiling code for a list of VM state numbers. And here in module, which indicates that the error occurred in a particular module here. So the JIT compiler module, and the method being compiled indicates the Java method being compiled. So you can see the methods here. Visit method and JIT tree method declaration. Now we are focusing on intermediate code generator in JIT compiler. You can see the intermediate code generator here in this diagram. It generates intermediate code. After generating the intermediate code, we can consider about code optimizer. It optimizes the intermediate code for better performance, and you can see the code optimizer here. There are several optimization techniques: null check elimination, branch prediction, loop unrolling, inlining methods, etc. And in this example, we are focusing on branch prediction. If you have a code like this, and if there's a difference balance, both branches of if condition hold, but one happens more than the other, the JIT compiler can reorder them according to the most common one and significantly reduce the number of assembly jumps. Now here it be assuming that most of the time x less than y, the condition will be flipped to statistically reduce the number of assembly jumps. So here you can see the flip here, and to reduce the number of assembly jumps basically. So and now after optimizer we move to target code generator. This converts intermediate code to the native machine code. In this diagram you can see target code generator here. So here you can see that with regard to the previous code, this for the optimization you can see the comparison instruction in assembly here, and you can see the jump instruction here. Here this assembly instruction mean jump if greater or equals is corresponding to the else statement in the optimized code in branch prediction. Now we move into Profiler. Profiler finds the hotspots code that is executed repeatedly. This is a tool which is the part of JIT Compiler. If is responsible to monitor the Java bytecode constructs and operations at the JVM level. In this diagram you can see Profiler here. If the value of sum were to be retrieved from and stored back to main memory on every iteration of this loop, performance would be dismal. Instead, the compiler will load a register with the initial value of sum, perform the loop using that value in the register, and then at an intermediate point in time store the final result from the register back to main memory. Yeah, and so here the sum will be, the increments will be performed through a register and move back to the main memory in the end of the operation. So this is a hotspot. Now we are moving into garbage collection in execution engine. Automatic garbage collection is the process of looking at heap memory, identifying which objects are in use and which are not, and deleting the unused objects. An in-use object or a reference object means that some part of your program still maintains a pointer to that object. An unused object or unreferenced object is no longer referenced by any part of your program. So the memory used by an unreferenced object can be reclaimed. In this diagram you can see three stages. In marking, this is in marking, this is where the garbage collector identifies which pieces of memory are in use and which are not. Here before marking, after marking it identifies a live object here and unreferenced objects here and memory space. Then step 2, normal detection. Normal detection removes unreferenced object, leaving reference objects and pointers to free space. So after normal deletion, you can see the structure here. Memory allocator hold a list of references to free spaces and searches for free space whenever an allocation is required. And deletion, stage 3 is the deletion with compacting. To further improve performance, in addition to deleting unreferenced object, you can also compact the remaining reference object. By moving reference object together, this makes a new memory allocation much easier and faster. Here after normal deletion with compacting, you can see the free space is here, and memory allocator holds the reference to the beginning of the free space here and allocated memory sequentially then on. You can also manually trigger garbage collection, but it provides no guarantee that garbage collector will actually run. You can call system.gc method, and the detail message gc overhead limit exceeded in out of memory error indicates that the garbage collector is running all the time and Java program is making very slow progress. After the garbage collection, if the Java process is pending, more than approximately 98% of its time doing garbage collection, and if it is recovering less than 2% of the heap and has been doing so far at least 5 compile time constant consecutive garbage collections, then java.land.out of memory error is thrown. This exception is typically thrown because the amount of live data barely fits into the Java heap, having little free space for new allocations. Now we are focusing on Java native method interface, which is communicated with Java runtime areas and execution engine and Java method library. Java native method interface is a standard programming interface for writing Java native methods and embedding the Java virtual machine into native applications. The primary goal is binary compatibility of native method libraries across all Java virtual machine implementation on a given platform. Here you can see a JNI interface pointer is here. This per thread JNI data structure here, and this pointer leads to array of pointers of JNI functions, pointer, and this pointer leads to another interface and interface function. This pointer leads to another interface function. This pointer leads to another interface function. Likewise, here in you can see in Java code, Java method call a function in C or C++ code, and this is a shared object in C or C++ code through and this and it returns the result. This call function and return results happening through JNI header file here, Java JNI in this diagram. Here in JNI in the statics block, my JNI native library is called in for example in my JNI.dll in Windows, so libmyjni in Unixes, and here this JNI program declares a native method say hello that received Java string and returns a Java string, and here the main method invokes say hello. Yep. And unsatisfied link error thrown if the Java virtual machine cannot find the appropriate native language definition of a method declared native. Now we are focusing on native method library, which is communicated with native method interface. This is a collection of native libraries which is required for execution engine. Native method libraries are libraries that are written in other programming languages such as C, C++, and assembly. These libraries are usually present in the form of DLL, .dll or .so files. These native libraries can be loaded through JNI. In this diagram you can see the JNI is here and C++ is native libraries are here, and Java code is here. It's communicate through JNI. In JNI environment, access via the argument this one JNI environment provides function for the conversion to get a C string JSTRING from JNI string JSTRING invoke method const char strict dot get string ufs chars, and then to get the JNI string, J string from C string, char strict invoke method, J string new string UTF. And in C implementation here, step is as follows, and it received the JNI string J string and convert into a C string char strict via get string UTF chars, and it then performs its intended operation, displays the string received and prompt the user for another string to be retrieved. Get string char, yeah. Then here prompt the user for C string here, printf, and this is a string, asking user for string to be returned. And in step 3 here, it converts the returned C string char strict to JNI string J string via new string UTF and return J string to with the return statement here. So this is the native C code for the compilation, and in the native library, native method library, and this can be compiled into a shared library. You can see here an exception example in JNI exception. You can see the file of the C code here, line numbers and reason for the exception, and you can also see the Java stack trace here. This is the end of the presentation, and thank you very much for viewing it.